summary for the previous week. That helps you, again, to review the material for your exams. We talked about synchronization, which is when you have more than one process running or more than one thread running. What were the strategies that were used? We looked at mutual exclusion locks and semaphores. So do understand how these algorithms work. What does one have over the other? So if you have it in a question, you could know right away, this is a semaphore, or this is a lock. Or this one has a condition variable with monitoring. So those are quick ways then to determine what it is you're working with. But the bottom line is that you have to have one process to continue or do some processing as another process waits. And also there's critical sections and race conditions that are taken into consideration. The critical section is where there is some code that has to be completed by this process. It cannot be interrupted. And race condition means one process has to be completed before another process can continue if they are related and one depends on the other. They're codependent. These are the topics for Chapter 6, so make sure you understand these topics, have a brief summary, a brief understanding, and that'll help you then, again, as a review guide for the exams. Chapter 7, we talked about deadlocks. When is there a deadlock? Well, you have to have some strategy so a deadlock does not occur. You have to prevent them from occurring. And also you have to recognize if it does occur or what it is you need to do so it does not occur. And these are the topics, so make sure you do, again, review these topics so you have a good understanding. And again, it'll be a good review then when you study for your exams. The midterm exam is in week 8, and it is chapters 1, or the weeks. All the chapters that are covered in weeks 1 through 7, the exam is based on the textbook. And it actually is the test bank that comes with the textbook. So that's why I'm giving you some questions as we go along that may or may not be on the exam, but they give you a good indication of what you will be, kind of questions you will get on the exam. Okay, any questions on week 4? Anybody? Okay, just to recap, if you want to get additional credit on the week 4 programming assignment, then do submit another item. The options were a flowchart for teaching assistants, running the Sleeping Barber program, or just offering some code, Java code for the sleeping teacher assistant, or actually have a running program for the teaching assistant with screenshots of the output screen. So you all are sharing these strategies in the discussion forum. You all have put down some of the items that you created. So do review your classmates' posts, offer your comments or your questions so that you understand it. And again, look at what you did. Are you missing something based on what your classmates posted, or are they missing something based on what you posted? So share with each other any issues that may exist between what you posted and what they posted, and this way you'll all come up with the same conclusion. And again, if you have the extra time, eventually do program it. Programming is a good skill, and the only way to get good at programming is by practicing and doing it. So depending, again, where you want to go with your career and how much time you have, you know, continue going on with that. So any questions on week 4? I'm not getting any response. Any questions on week 4? Other than there's a lot of material and you just have to know it. Any questions? Hello, are we there? I think I locked out you from typing. There we go. Okay. Again, I have these options so you can talk, you can use your webcams, and you can type into the chat box. Now we got to go. It was locked out. Right? Okay, good enough. Thank you. And again, if you ever do have any questions, again, go over the exercises at the end of the chapters, review the topics, and then also understand. You need feedback on your work. Your feedback for what? Your programming assignments for week 4? Is that what you're referring to? Okay, then I will then put together a, well, you do have the pseudocode from, or at least the actual C programming code. So I do recommend you take a look at that. That is the actual program. If you like, then I will look to see who maybe has posted the flowchart closest to that logic, and then I will then post something in the discussion forum for you to use as a reference. Good idea. Okay. But again, don't stop from looking at each other's code. Okay, a lot of you already have the answer, more than you think you know. But the answer is there, and also those of you who completed the program, you definitely have the answer. So please share that with each other. So your answer is there. I will then give you another version of the answer, I guess, for you, or point out who has it correct. Okay, now onward to week 5. You're welcome. I will do that then. You did mention that last week, and I just was assuming that you're going to look at what your classmates post and know then who has the correct answer and who does not. So maybe, yeah, you're right. Maybe I should give you some guidance and direction on that. But the key is look at those who actually programmed it. Whoever actually programmed it and has an output screen, those are the ones that did get the logic correctly. Okay. Okay, so I will be doing it either later today. I will try to get to it later today, my time, which will probably be your time tomorrow. Okay, so week 5 assignment. We are now going into memory management strategies. Again, a lot of different strategies. But in any kind of operating system strategy, if you look at it from what is done with the simple technology to what is done now with our more sophisticated technology and demands. That is the evolution of strategies, and that is the evolution of algorithms. They had to deal with more complexity. That's why new strategies were then created. So if you keep that in the back of your mind and relate whatever algorithm or strategy you're looking at related to the complexity that is appearing or that is required, that'll then give you an overall picture of the history and evolution of these algorithms and strategies, but also allows you then to see why there are more complex strategies. So you can put them in a ranking and in an order as to how everything evolved from a technological standpoint and from a programming standpoint. More needed to be done, so that's why this was added. So it's kind of a little stepped procedure from one to the next one to the next one. So if you see how one got more complex when the next one was created, and then the next one got a little bit more complex, it's these little variations that were added that gives you a clue or an overall picture of what any individual strategy or algorithm is. So as you go through week 5 topics, first of all, here exercise 811 kind of has you go through some of the various strategies that are used. It was contiguous memory allocation to segmentation to paging. So this really gives you by answering this question, you will get a good glimpse into this historical evolution of these strategies. So if you keep in the back of your mind what we are able to do with the computers before, what we need to do with the computers now gives you a clue as to why there is these new strategies or why there are multiple variations between strategies. And then exercise 816, again, you're looking at page tables, a very important topic. You even have an extra video on that and a PowerPoint presentation on page tables or paging. And I also added some videos on the announcements page. One is a very good video. I have the link on these slides as well. If we have some time, I'll maybe let it play. but it gives you a good overview and also some visual animation that maybe will help you understand this evolution and how things change and what is being done now with all the memory. Again, you have fixed amount of memory in your computer, but you have a lot of demand for this memory. So what are some ways to deal with it? How can we satisfy the user as well as be able to accommodate the demands and requests by the user and from the user? A lot of it is dealing with searching when you have memory. It's not only just getting information into the memory so the CPU can process it, it's also the strategies as to when it can be used or when it's okay to wait and not use it and let someone else use it. So this is another exercise that allows you to look at a couple different strategies for paging. And then this exercise, this one you can program if you have the time to do so. I did already give you the algorithm for this in the office hours. This is discussed in your textbook. But it will allow you to pinpoint where something is then is located in memory. So it's just strategies to, when things are put into memory, there has to be some way to find it, to know what is where, what block of code is in what location in the memory. So these are the strategies then to arrive at that address, because obviously when you are processing or when the CPU is executing the program or process, it needs to know its next piece of instruction and it needs to get it to the CPU. So in order to get it, it has to find it so it can pass it. So that's what these strategies are. You got to keep track of what is where in memory and then know which one comes next. It kind of combines your process scheduling with your memory management. So your options, again, you can offer this in pseudocode, the algorithm for the calculation necessary for the answer in pseudocode. Again, various options for this program. The ultimate, obviously, is to run it. So I do have this in the discussion forum, so you guys can discuss your strategies on this and maybe arrive together on a program that you will all then complete or work on together and complete it. But this is the input. You have a value that is input, and you need to get this output. So I will be discussing a little bit about this, but here's the algorithm that is used. This is the answer that you get. So you have the input, you have the output. So in other words, you have the answer, and this is now the algorithm that is used. And this is in the discussion. So if you want to discuss this together as a class, please do so. What are your strategies for this Java program? What are your, in any program, when you do design or create a program, you have to plan it. And you have to start identifying some parts of your program that you need to include. You're going to have input, so then you need to create variables for this input. You're going to have output, so you need to create variables for your output. And then when you do have input, you need to determine what you do with your input. So what is the algorithm for your input? And then how will you ask the user for the input, as well as how will you display your output? So these are basic things that are included in every program. But this one, again, it's a simple program that you probably can do, so I would urge you that you do it. But again, a flowchart, pseudocode, or Java code for this program will suffice for the answer. So get it as close to a program as you can. The more you do, the better off you are in learning new skills. And this discussion is in the discussion forum, so you all can work together on this. Any questions on this part? I don't know how much time you have to go over the readings and go over what you need to understand, but it looks like you all understand it, so now you can go at it. Okay, memory management strategies. So you have a lot of algorithms, and I know you will do your best. And again, if you have more heads working together, more brains working on this together, then the answer will be done. So that's the same thing with the week 4 programming. Work together on it, those of you who completed it. Help those who did not complete it so that they can understand what they're missing or understand it further so they can program it. So hopefully you'll work together on that. And then I will also point out, at least upload the programs that were completed by your classmates. if they have not already. Okay, so memory management strategies. Each approach has its own advantages and disadvantages. We know this already with anything that we look at on the computer. Some things just work better than others, but it all depends on the situation you have. So selection of a memory management method for a specific system depends on many factors, especially on the hardware design of the system, and that is because you're dealing with memory locations, and you're dealing with a fixed set of memory. So how do we allocate this memory? That's what the operating system does. We know that when a computer runs, there are already some programs that are running and being executed of the operating system, so you can use your computer. So that definitely has already some of the memory that's used, and then there's some memory then available for your programs or any applications that you run on a computer. So many algorithms require hardware support, leading many systems to have closely integrated hardware and operating system memory management. Because it's the operating system that actually is placing those items into the RAM. And so there has to be some close integration between the two, and also the operating system has to keep track of what was put in what memory unit. So in general, when a program is run, hopefully you already know that the CPU can only access information from registers or RAM, and only depending on your CPU, depending on how many instructions can be run and what each instruction involves. Sometimes it involves data, sometimes it doesn't. So there's a lot of processes that need to follow through when any instruction is executed. So things we're going to talk about is contiguous allocation, paging, segmentation, combinations of paging and segmentation. Although they differ in many aspects, all approaches must guarantee that every memory address generated by the CPU must be checked for legality and possibly mapped to a physical address. Now remember, even when you are working with memory addresses, the processing of that address has to be done by the CPU as well. So it's not a matter of just getting data or instructions from the RAM or from memory. It also has to process the addresses of where that data or those instructions lie. So in order for memory addresses to be even recognized, they have to be processed by the CPU, even though they are needed for the CPU to continue and process an instruction. So it's kind of double-fold here. In order to give an address, the CPU has to understand, process, and generate that address at the same time. But in general, a typical instruction execution cycle, for example, fetches an instruction from memory. The instruction is then decoded and may cause operands to be fetched from memory data. After the instruction has been executed on the operands, results may be stored back in memory. So there's a lot of sequence between the use of memory and then the generation of addresses for these locations in memory that are used. So there's a lot of processing that's going on. And there has to be some kind of manager to keep track of all these addresses and what is where in these addresses, to know in what order these addresses are passed to the CPU or generated from the CPU to then locate the data or the instruction. In the old world, in the old way, in the simple computers, again, I didn't mention how this is an evolution from simple processing to our complexity that we have today. In the, our first computers, or the older computers, we had single tasking. So it selects a process in the input queue and loads that process into memory, and then it processes the instructions in the data from the memory, and then when it's done, the memory is then made available for the next process. So that's great. However, we don't work that simple anymore. We don't want to wait for things to process that simply, so we wanted to add complexity. But one thing that is across the board, no matter what strategy you have, we do use symbolic addresses. In our programs, we use symbolic addresses. For example, a variable. When you name a variable or declare a variable in your program, that is a symbolic name for an actual memory address. Now, when it is actually assigned a memory address, can be done in different times of the execution of a process. It can be done when it's compiled. It can be done when it's linked. Or it can be done when it's during runtime. So that too needs to be determined. What statement can have an address right away assigned to it, or need an address right away assigned to it? What statements can wait for the linker? What statements can wait to be done during runtime? So it goes hand in hand. Sometimes that address needs to be given right away so the process or program can continue, and sometimes the process or program can wait before it's assigned that memory address. So if you know a compile time where the process will reside in memory, then the absolute code can be generated. In other words, the actual address. And that would be dealing with your registers. Now, you don't know that. It's the compiler who does that. The compiler, any program is compiled, and in essence, it's translated that into machine code. And it's during compile time that's already known what statements are needed addresses right away, and which statements do not. Load time. If it's not known in compile time where the process will reside in memory, then the compiler must generate relocatable code. So it's not until the actual process is loaded that additional addresses then are assigned. And then there's execution time, and that's when it's actually running, that is given memory. So it all depends on your program, what you're doing with your program, or what the process is doing, and when it is compiled or loaded or executed determines then what statements or what data structures or what processes need addresses right away, or they can wait. So generated addresses, there's a distinction made between logical and physical addresses. Physical addresses is the actual location on the memory chip. Logical is what we use. In other words, it's our symbolic type of addressing. When we have an array, we know that we have the first item in an array starts at 0, and then depending on how large the array is, we'll have an ending point. That would be our logical version. We would address it and reference it symbolically. However, it is translated into an actual physical address. Okay, so compile time and load time, that we know already, that we need addresses right away. Execution time means we don't need it right away, so they can be different. Sometimes they're the same, sometimes they're different, depending on when they're needed. So we have a physical address space and logical. Again, logical, you can think of symbolic, you can think of virtual. Physical is actually location on the memory chip. So that's a distinction between the two. We work in the logical world. The computer works in the physical world, and then there's always some translation. There's a translation that needs to be done from the logical to the physical, and depending on when that needs to be done is determined by the kind of statement or process that's being done. So it will be determined if it's during compiling, loading, or executing. So that is on a basis of what it is the programmer is doing. Is everybody clear on that? Do you know, at least understand that there is a difference between logical and physical? We work more with the logical world, and then the physical is the actual hardware. Are there any questions on that? Because this is important for later discussion where we then need to map. Okay, so we know there's a logical address, there's a physical address, and then there's a lot of strategies on how do we go from our logical world to our physical world? And that's where we have all these tables. This is where we have all our mapping and keep track of what it is we're referencing in our program as opposed to where it actually exists on the memory chip. So we have a memory management unit. So again, as I mentioned, the user program deals with logical addresses. It never sees the real physical address. However, there has to be something that makes a connection between these two, and that's your memory management unit. So the runtime mapping from virtual to physical addresses is done by a hardware device called the memory management unit. The base register is called a relocation register. Registers are forms of memory, or units of memory. And then there's a strategy here. Again, we work, as I mentioned before, with our array. We start always out, our first array element is always 0. But it doesn't mean that it's mapped to a physical address of 0. No, there is some kind of calculation here, because on the memory unit, it starts at 14,000. Our logical array starts at 0. So it maps. So it adds 14,000 to that 0, so that that first location, even though we reference it as the first element of array being, your subscript of 0, in actual physical address is actually 14,000. So there's a mapping here, and there's actually a hardware device that is responsible for this mapping. Here's your example here. We have the logical address, where the array element is 346, and we know that everything starts at 14,000, not 0, so then we add that 14,000 to our 346 to get the actual physical address. So that's how the operating system makes sense out of your logical address to the physical address. Now, dynamic loading and linking. This is a way then to, again, evolution. First of all, one process was put into memory, it got processed, and then memory was freed up for the next process. Well, we don't want that to happen anymore. We want more processes to be working at the same time. So how do we do that? Well, one strategy is to keep some of the program or process out of, in some other external storage device, and then only bring it in when we need it. So we know we got to have it, we know we need it, but we don't need it in memory all the time while that process is being executed. So since we don't need it there for every step of the process, we can keep it out on some external device, and only when we need it, bring it in. And then we have like the stub. The stub is like a placeholder. So we know it has to be there. We don't need it right now because it's not really being executed yet. But we want to keep the order of things. We know that has to be there when we go through an order of processing, or executing this process. So it's kind of a placeholder. And then later, when it's needed, then that placeholder then is where then the actual code is brought in when it's needed. So these are placeholders just to, again, not use all the memory up. We have a fixed amount of memory, so we need strategies in how to use this memory. So we're going to have placeholders instead of all of the code sitting in memory, because then we won't have enough memory. But this way allows us then to use the memory at a placeholder, and when it's time that we need that actual piece of code, it is then given more memory. So it's kind of delaying it with a placeholder. So dynamic linking and library, very heavily used in the programming world. You actually would have libraries that you will use. In other words, it's when you use a function in a program. When you write a program and you use a function or a method, you just write in the method name. You don't put in all the code that belongs to that method. No, all that code is left in the library. And it's not until it's actually needed that all that code is brought into your program. So that's, again, a strategy to reduce the demand of memory at any one time, and just having that information come in when it's needed, or filled up when it's needed. So here's a example or a graphic that displays all the different types of addressing requirements. Compile time, we know it's giving addresses right away. Load time, and then execution time. So this is typical of how when we write a program and how our programs are then compiled, linked, and then executed. So that is the process of any program. If you've done some programming and looked at the process that is that happens anytime you use and run a program. You have your source program that you write in the text editor or graphical editor, depending on what kind of programming language you use. You then have to compile it. You then have to link it. You then execute it. So this kind of mirrors the process you go through when you actually create a program and run it. Okay, swapping. Kind of similar to the stub strategy. But what that means is you swap in pages or swap in code that you need so you can share memory space. You have a backing store, you have a rollout, roll-in store, so different strategies for swapping, but in general, you swap in and swap out code when you need it. Kind of goes along with your code for your library. It's in the library and it's not put in to your code or into memory until you actually need it. Now this is dealing with processes, so it could be more than one program that's running. So again, it's another evolution. We have already we found some strategies here that say, okay, I'm going to use libraries, leave the code in the library until I need it. Okay, that's good for one program. Now, what if we have more than one program? Well, okay, it's kind of swapping. It's kind of like leaving it in a library, but you're putting it somewhere. You're putting the code somewhere. It's not necessarily designated library, but it's another location that it's going to go until it's needed again and swapped in and swapped out. So again, if you look at the evolution of what it is that we want to do with our computer and what our demands are, will kind of give you a clue as to the evolution of these strategies. So we have contiguous memory allocation. Now, how do we actually allocate this memory? We have different strategies between what we do with this, either one process, or we have dynamic, or we have swapping. Okay, well, now let's talk about these blocks of memory that we're using. It can be used for anything, any strategy. But right now, we have contiguous memory allocation, which has partitions. Your operating system, I did mention before, when you have programs running or your computer running, you have some of the operating system programs are in memory and running at the same time as you then want to process your application. So you're sharing your memory. And there's something that's called partitions. Has anybody partitioned their hard drive? How many partitions do you have on your hard drive? So you have partitioned it. Good. So that gives you an idea then how this is handled and how you partition a hard drive is similar to how main memory is partitioned. So similar strategy in that you have reserved areas or you have something on those areas for that purpose. So resident operating system usually held in low memory, and then user processes held in high memory. You can specify the size of these partitions. When you have an operating system, usually it comes with a default setting, but you can change these partitions if you want. Sometimes the operating system is in memory, but not all that operating system, it's given like a chunk of memory, but it doesn't always use all that memory. There's a lot of free space. And if you have intensive applications you're running, excuse me, if you have intensive applications, you maybe can take some of that memory, change your partition size. So these are some things that you as a user can do if you wish on your computer. It's not always a matter of running out and getting more memory. You may be able to use the memory you have, and just change your partitions. And then when you have these partitions, obviously you're going to give a chunk of the memory and allocate it to a process. Here's some examples of an evolution and how processes, when they go through, in the first diagram, you have process 5, 8, and 2. 8 is done, so that block of memory is freed up. You then have 9 come in, and you have 9 doesn't need the same amount that process 8 did, so we have more room, and we have process 10 coming in. Again, the video I put on the announcements page has some nice animation with this to help you understand how this works, so I do urge that you do look at that video. And then dynamic storage allocation. Okay, we have this free memory. How do we put stuff into this free memory? There's first fit, best fit, worst fit. Similar to our priority and preemption strategies when we look at processes. Again, a lot of it relates because we have a fixed amount of resources that we need to allocate. So how do we do that? So these are some strategies that can be used, but unfortunately you can have fragmentation. In other words, you have these free memory spaces broken into little pieces. Again, this could be likened to a hard disk. How many of you do disk defragmentation on your hard disk? The system tool, that is a tool that's needed so that your performance on your computer and access of your files is done at a smoother pace. Does anybody use this defragmentation? Or how many use some basic system tools for your computer? Is there some routine maintenance that you perform on your computer? Some things are disk cleanup. Yeah, there's disk cleanup, disk defragmentation, some similar ones. Okay, so it's something that you need to do and do on a routine basis, so you can set up the task scheduler to do it automatically for you. But this is very similar here. When you start using these strategies, go back here, dynamic storage allocation, depending on the strategy you use, may cause some fragmentation. You have little pieces of memory space, and it's not good enough for any process. So what do you do next? Break up the process. That can get very complex and very crazy very fast, keeping track of all of that. But when you run a program, we have a lot of things that are running, a lot of demands. Good, I'm glad you looked at the video. But we have a lot of demands when we have a program. You have subroutines, you have stacks, you have symbol tables, main program, square root, a function. So how does it put into memory? When you have segmentation, and we'll talk, there's a difference between segmentation and paging, and the main difference is segmentation will use variable amounts of memory blocks, whereas paging has a fixed amount. It's an actual page that has a fixed amount all the time for everything you're doing. But the reason it does that is that way it eliminates fragmentation. Segmentation, as we're looking at, you already know you can have some fragmentation. If you looked at the video, the graphic here, 8 is a large hole, but then when 9 comes in, it only needs a piece of 8, where 8 used to be. But then once you start switching this in and out, say the last graphic I processed 5, 9, 10, and 2, but then I have another process 11 coming, and it needs a larger group, a larger block of memory. So what happens? It never processes. So again, these are just strategies, again, based on our demand on the resources. So segmentation is where they're variable, but it can lead to fragmentation. Paging is a way then to eliminate this kind of problem. In other words, we don't vary memory chunks, we just give a page. And this is what one of your exercise questions deals with, paging. So you have a certain size. You have a page number and an offset. In other words, you start at the beginning of a page, but you may have part of that page or not all of that page. Even though you're allocated that entire page, you may not fill up that entire page, so you have to have a way to find it where it is on that page, and that's what's known as your page number with your offset. So here's some graphics for your pages. Again, we all have to map it from our logical to our physical. We have numbers, we have tables that keep track of all of this. Again, it's just you. Just think of you had to do that. If you had to allocate, I don't know, in your real world scenario, Think of it as blocks of time. How do you allocate your blocks of time? Well, if you have to do something and it only takes 5 minutes, you're not going to give yourself a whole hour to do it, are you? Well, if you do segmentation, that means no, you won't. You'll give yourself 5 minutes for the 5 minutes you need. But if you're doing pages, you'll give yourself, if all the pages are 1 hour, then you will give yourself a whole hour for only that 5 minutes of processing. So then we see that's another problem again. Why give yourself a whole hour of time when you only need 5 minutes? So then now there's strategies to deal with the pages. Well, maybe we can share pages. Again, when you share pages, you have to keep track of it. The more pages you have and the more sharing you do, the more complex it gets. So another more strategies came up with hierarchical, hash page table, and inverted page tables. Again, just strategies. Again, if you want to liken to it, okay, segmentation gave you varied amount of times. If I needed 5 minutes to do that job, then I'm given 5 minutes. However, paging gives you that a whole hour because every page is in an hour. Well, that doesn't make sense because we're wasting a lot of time. So what do? Let's see how we can figure it out. Well, let's have pages and pages. So we're going to break up that hour into blocks of 10 minutes. But we have to keep track of it because we're going to be sharing it or have a lot of processes running. So it's a 2-level page table scheme is one area, and then there's 3-level pages, so you can have pages within pages within pages. Now, something that is difficult and complex to not only write a program, but also to make sure the program is correct and doesn't, again, you can't confuse these issues. You can't confuse these memory blocks and give the wrong data to the wrong process, for example. So if you want to think of 2-level page table, it's kind of like a loop within a loop. I don't know if you worked with nested loops when you did any programming, but it's like a loop within a loop. So you have to keep track of your table page within a page, your table within a table. So that's your 2 levels. And then you have a 3-level. Here's a 3-level. So you have page within a page within a page. So again, a lot of this complexity is just to try to manage your memory to the most efficient and productive way. It started off, well, one process uses it, and when that process is done, then the next process can come in. But that was not efficient when you want to do more processes at the same time. So then you start blocking off your memory, sharing your memory, segmenting your memory, and putting your memory into pages. Hash page tables. These are created. It is a way to use a hash algorithm. Hashing is popular and it's being used only because when you are searching through memory for something, you have a lot of time that's taken to search for something. If you are in a table, this gives you an algorithm to put it into a table and you might find the memory location faster. There are faster sorting algorithms used for hashed items. So this is an example. This is very, again, used not only for hashed page tables, but it's also used on the internet for any kind of encryption, decryption, a lot of database, any kind of database storage. So a lot of these items are used, these strategies are used in various areas. But here's an example of the strategies for a hashed page table. But bottom line, you still have a table that keeps track of your memory. This is just how to get from the logical address to the physical address. There is some value added to the logical address that will then bring you to your physical address. Inverted page table. Instead of keeping a table for your logical addresses, you keep a table for your physical addresses and map it from that direction. So a lot of different strategies are used. Is one better than another? Well, there's slight improvements. So do know the difference between the two. Why one was created when you already had one strategy? Why create this next strategy? What are its benefits? And that'll give you a key as to how it functions and what it works and why it was created. And here's a little difference between paging and segmentation. Again, segmentation is varied sizes, paging is not. The varied sizes causes problems and causes fragmentation, similar to your fragmentation of your disk. So here's some comparison between paging and segmentation. And then here's the video that I offered you, and it is on the analysis page. So do look at that. It'll give you more animation to help you see this this evolution of strategies and why they were created. Okay, so any questions on week 5 material? A lot of material, but again, if you look at it as a historical evolution, because our demands have just become greater, and what to do with what it is we have, it's fixed memory. Unless you start adding, next week we'll be looking about virtual memory, where we're going to add different storage devices to extend our real memory. So we'll be looking at that. But for these strategies, this typically works with fixed memory. We're looking at it from the viewpoint of fixed memory. So are there any questions so far? Any questions? Again, a lot of material just to know. Again, strategies. You do have the midterm exam coming up on week 8. Exams are a large portion of your grade between the midterm and final exam. Do make sure you look at the topics. I give you the topics every week. Understand each of those topics. I do give you extra questions. Do know and understand and look up those questions. I even give you the section number to look at to understand that question. So as you revisit that material, you not only understand the answer to that question, but about that topic that is part of your question. And review as much as possible. I do review the previous week twice every week, and also the discussion forum if you have questions. Do the exercises at the end of the chapters. If you have questions, bring it into the discussion forum. Or if you want the answer, say you worked on this question, you want to know if you have the correct answer, put it in the discussion forum so then I can, we can discuss the answers. We will have a review session, so we'll be going over both office hours and the virtual session. We will go through the chapters and review them. The office hour will have the first set of chapters, and then the virtual session will have the second set of chapters for the exam. So be ready with any questions that you have, and depending on the time and the questions we have, we'll try to fit it in. But again, we'll have the discussion forum to discuss any questions you might have. So yes, there's a lot of material. Use the strategies and the learning tools that work best for you. And hopefully that'll give you then, a good understanding of the material, and that you will be successful on the exams. In the discussion forum, I will look at the week 4 programming assignment, give it to you as well, or point out what's already there. Some of you did complete that program. If you didn't upload your program, please do so for the rest of the class to see. If you only got partial credit, then do submit another item. And again, there was the variety of items with a flow chart, the sleeping barber, Java code for the sleeping teaching assistant, or the actual program running. So those are your options. If you want to get that extra 10 points, please do then submit the material. And for this week's assignment, work together. It's in the discussion forum, so work together on this program so that you all can give me then a program for your answer. That would be wonderful. Work together on it. And the exercises themselves, these are good exercise questions, and they kind of give you a look at all these strategies at the same time. So these are good exercise questions to give you a good foundation for the material for this week and this chapter. Okay, and with that, again, I'm going to do part, hopefully everybody's still here, because right now I'm going to be saving a list of participants that are here. So if somebody left, tell them then to let me know they were here. Hopefully you didn't leave, you're all here. Wait, I'm going to save this. I don't know if you're seeing my screen on your screen, but I'm just saving the participation list. Okay, so good luck with everything. If you have any questions, post them in the discussion forum. Any questions now? Are we all good with everything? You're quite welcome. And again, as I mentioned at the beginning of this session, as you were all starting to come in, you're all doing a great job, really. I do commend you on your persistence, your diligence. You really take your education seriously. I think you're going to be very successful in this course. But just keep doing what you're doing. You're doing wonderful. And any questions, again, use the discussion forum. Assignments are due Saturday, as usual, Saturday evening. Sunday starts week 6. And just to give you a heads up, in case you want to get started, here's the questions for week 6. And again, one of them is a programming assignment. So hopefully you're going to get good at flowcharts, pseudocode, or actually code to do the best. All right, thank you. Have a good evening.
Recording stopped.
We will see you next Monday for office hours of week 6. And we'll see you in the discussion forums. So long.